In recent lecture A's of differential equations in linear algebra, we've been focused on forced damped harmonic oscillators. That continues a little bit at the beginning of this lecture, looking at sinusoidally forced damped harmonic oscillators, but I want to really use this as an opportunity to introduce a numerical differential equation solver in Mathematica called NDSolve, a built-in function that will help us numerically approximate solutions better than Euler's method does. Then we'll also move on to linearization. I talked about linearization in the van der Waals system last time in 29A. I'll talk about it here in 30A. I'll talk about higher dimensional linearization in general, give you the basic idea of it, and then we will apply it to a two-dimensional competing species model. All right, so let's talk about the phase plane for the forced harmonic oscillator. This also affords the opportunity to re-emphasize that when you have a non-autonomous system of differential equations, as this will be, your solution curves in the phase plane can actually cross themselves, and that will happen here. It's with autonomous equations that they don't. So here's our general second-order harmonic oscillator. That's a linear ordinary differential equation. The second derivative of y with respect to time twice, plus p times the first derivative, plus q times the function itself. I've been using a cosine of omega t, but we could use a sine of omega t. Let's stay consistent, though. First thing I want to emphasize is that we can convert this to a system, a non-autonomous linear system with a time-varying vector field. Here it is as a system of two scalar equations. Essentially, this first equation is just a definition of what v, the velocity, if you will, is. It's dy dt. The second equation, you differentiate both sides of the first equation, and you use the harmonic oscillator equation, solve it for the second derivative of y with respect to time by subtracting qy and subtracting pv from both sides to get this, and you still have the cosine of omega t in that term. This can be converted to vector form as a vector field. This parametric curve, y is a function of t, its derivative is this time-dependent vector field that equals this, that can be split up into a linear part. And while this is a nonlinear part, however, it's still a linear system because that nonlinearity is occurring in time. The only thing that you need for linearity for a system of differential equations like this is linearity in the vector y, in this case, whose components are little y and little v. It doesn't matter that cosine of omega t is nonlinear. Symbolically solving this on Mathematica, as I'm about to show you, in the general case where p, q, and omega are arbitrary, can be done by Mathematica, but involves an incredibly complicated formula. You would not want to solve it by hand for the general case. Maybe, in spite of the fact that we can get a solution, we'd prefer a numerical approximation, and that will definitely be the case in our Chapter 5 nonlinear systems. We definitely need numerical approximations. Maybe something more accurate than Euler's method would be good, because we did see in the past, Euler's method is certainly not the most accurate method that there is. It's the simplest, but not the most accurate. So in Mathematica, we're going to use NDSolve. There are related functions. There's an NDSolveValue. There's a parametric NDSolve. But let's just keep it simple and focus on NDSolve. Remember, as I mentioned a couple minutes ago, solutions for such a non-autonomous system can cross each other, or solutions can cross themselves, as we will see. This actually does not violate the uniqueness theorem. That's just a reminder. All right, so let's move on to the Mathematica and take a look at what we can see here. So first, I've got DSolveValue. I'm attempting to solve the differential equation symbolically. In the general case where p and q are unspecified, this is going to give us a general solution. I'm not giving initial conditions for this one. If I enter it, it does produce an output, but that output, as you can see, is incredibly long and complicated. Yikes. Certainly would not want to solve that by hand. Can it be simplified? Possibly, but let's not worry about it. What if I add in arbitrary initial conditions, y of 0 equals y sub 0 when I would write that by hand, and v of 0 equals v sub 0? It's still pretty complicated. It still can be done, but it's still pretty complicated. So the point is, we would like to avoid those things. Numerical solutions of the IDPs can be found, as I've said before, with Euler's method, but now we want to use a built-in function called NDSolve. So here's the syntax. This clearing solution is just going to be a standard thing I do to make sure that memory is not messed up. Here's the basic syntax. instead of DSolveValue or just DSolve, I'm using NDSolve, capital N, capital D, capital S. Inside the square brackets, what goes in the initial list is your system of differential equations and your initial conditions. And if I want to use it like this, in the way that I'm doing, I have to have specific initial conditions, not arbitrary ones. There will be a way that I'll show you how to do it with arbitrary initial conditions. There's my first derivative equation, dy dt equals v. Here's the second one, dv dt equals negative 2y plus cosine. I picked omega to be 1.56 here. In fact, I picked it purposely to relate to lecture 29a and a graph that we saw there. So this does produce some kind of output, but it's hard to say, exactly what kind of output is that. Are these the graphs of y and v as functions of t? Well, basically, though they are not real nice looking, you can evaluate the solution when you have given it a name, as I've done here. I've called the output of this, whatever it is, these interpolating functions, I've called it solutions, and I've somehow stored the output in this variable that I'm calling solution. I didn't have to call it solution, I could have called it sol or something like that. That's my name for it. But once I've got that, if I, for example, want to evaluate the function at a certain moment in time, like time 1, I have to type y of 1, and then I have to type slash dot, and then solution, which is the name of this variable that I defined. And that will give me the value of this function at time 1, for example. I can plot the function. Here's the basic syntax, plot. This other stuff is just to make it look nice and also to make the interval t go from 0 to 100, which reminds me of something else I forgot to mention. You do need a specific interval of time here at the end of the NDSolve input. You also need the functions you're solving for in the middle here. But if I go evaluate square brackets y of t slash dot solution, that's extra funny stuff that you have to do to actually get a solution curve. And there it is. This is one of the pictures that I showed you in lecture 29a of the beat phenomenon in the case where omega was 1.56 and q, which is essentially the Hooke's law constant, was 2. Square root of 2 is about 1.4, is pretty close to omega. This is when you get the beat phenomenon. And we are seeing it here with a numerical approximation. Also thought it would be good to animate this beat phenomenon briefly here. Keeping in mind that when you see this, I can let it run here. There we go. What is the graph telling you? Well, if this red dot over here on the left was a mass and a spring going up and down, it is showing you the beat phenomenon graphically over here and with the motion over here. Sometimes the motion is a small amplitude, but then it gets bigger, and then it gets smaller. Here it's getting bigger. The amplitude's getting bigger, now the amplitude gets smaller. This can happen when you've got no damping, no friction, and omega and square root of q are close together. Now, does it typically happen with masses on springs? No. More typically, it's going to happen, for example, with sound waves. And the oscillation is representing air pressure waves over time, though the scale would be off on that kind of application. That would be a more common application. If you want to plot the solution curve in the phase plane, you can use ParametricPlot. And once again, you have to use evaluate, and once you've got your function in there, y of t comma v of t inside a list, you have to go slash dot and then the solution name. Again, solution is just what I called the output of NDSolve. I could have called it something else. This graph's a parametric curve in the phase plane, and yeah, that's certainly intersecting itself, it seems, many, many times. That's modeling the behavior of both the position, so to speak, and the velocity, if it's a mass and a spring, over time. It's going to be more clear how this goes if we animate it. Animate this as well, and I also animated the changing vector field over time. So we see the solution curve does cross itself, and we do see kind of the beat phenomenon because we have small oscillations at first, and then they get bigger, and then they go back to smaller, etc. That does not violate uniqueness because it's a changing vector field. It turns out to not violate uniqueness in spite of the fact that it's crossing itself. If you added an extra dimension in here, a third dimension for time, then it won't cross itself. It doesn't cross itself if we add a third dimension for time. Then time goes up this axis, and you can see the beat phenomenon in 3 dimensions here. as the spiraling gets bigger and smaller and then bigger again. If you look straight down on this graph, then you get the two-dimensional version where you see it looks like it's crossing itself. But if you add a time axis, then solutions don't cross themselves, and in fact, distinct solutions also don't touch each other. NDSolve allows us to also deal with unspecified parameters, like an unspecified p, q, and omega, and unspecified initial position and initial velocity, say, as long as I define solution as a function of those things. Notice the underscores as Mathematica functions require. I also put y0 and v0 inside curly braces. There was a good reason I did that I'll talk about here in a few minutes. This will solve it, but it seems to not produce any output because the reason is p, q, omega, y0, and v0 have not been specified yet. That's why there's no output. If I plug numbers in for those things, then I do get output. I get interpolating functions, and if I plug different numbers in, I get different interpolating functions. I can plot these things for picking particular values of p, q, omega, y0, and v0. P is 0, q is 2, omega is 1.56, y0 and v0 both 0. I get the same graph as before. Now, though, we can also bring, this is the most fun part, we can bring something called Locator into play with syntax that's kind of strange. You just kind of have to copy and paste it that you see here. To make an animation, I'm also allowing myself to change p, q, and omega with these kinds of symbols here. And Locator can change your initial condition. So I'm moving the cursor over here to change the initial condition. We still get a solution that crosses itself and over time does still demonstrate the beat phenomenon. It can still happen even if your initial conditions are not at 0. The way the locator pt for point here comes into play is right here. I have to put it in place of y0 and v0 when I use this syntax for the locator. And again, it's the locator thing that gives me the cursor that I can move around. A lot of times in Mathematica, you just got to copy and paste what somebody else has done, modify it, experiment with it to see if you can get it to work. It's not necessary to fully understand it to be able to use it. All right, let's go back to the PowerPoint. And let's start on the next slide here. So I introduced higher dimensional linearization in lecture 29A. I'm continuing that here in lecture 30A with more depth, okay? And also some reasons behind things. We did talk about in 29A the van der Pol equation, the second order nonlinear ODE. The nonlinearity in this case doesn't come from a cosine forcing function. I mean, it's 0, it's homogeneous. The nonlinearity comes from the x squared right there. That's the nonlinearity. Okay? It's a differential equation for x instead of y. It's not a big deal. If it were y instead of x, that would be a y squared instead of an x squared. That's the nonlinearity in the dependent variable that causes this differential equation to not have standard formulas for its solutions. It could have non-standard formulas that you've never seen before, but it has no standard formula in terms of ordinary calculus and pre-calculus functions that are called elementary functions. What's the corresponding first order nonlinear system? Still nonlinear. It's a vector field. It is autonomous this time. The previous one we were just looking at was non-autonomous. It depended on t on the right-hand side. Here we do not depend on t on the right-hand side, only x and y, a new variable that I'm going to introduce. But it is nonlinear. So dx dt, well, y is defined to be dx dt, just like in the previous one where I defined v to be dy dt. And once you've defined y to be dx dt, then the first derivative of y with respect to time is the same as the second derivative of x with respect to time. You can solve for it here. Same kind of thing we did with the harmonic oscillator. And get this down here. And once again, it's the x squared there, that's the nonlinearity. However, we can separate this vector field, this nonlinear vector field, into what you might call a linear part and a nonlinear part. Over here, we've got the linear part. Over here, we've got the nonlinear part. And this here could be represented as a matrix times a vector. We could think of this as the matrix 0, 1, negative 1, epsilon times the column vector xy. Based on things we've done before, that should be pretty clear. Okay? So a linear part and a nonlinear part. Don't worry about the epsilon. Epsilon is a real number. Think of it as fixed. Okay, we took epsilon to be 1 last time. I emphasized that for the main application, epsilon did need to be greater than or equal to 0 for the main application of this, which is to a certain kind of electric circuit. Here I'm allowing epsilon to be negative just for fun, you might say, because we might see something interesting in the phase plane as epsilon changes, maybe a bifurcation. That's what we're after here. But before we can talk about bifurcations, we need to talk about the corresponding linearized system. And when you say it's a linearized system, it's always at or near some equilibrium point. This system has only one equilibrium point. I am going to show you the null lines. It's at the origin. If you set this equal to 0 and solve for x and y, the first component being just a y means y would have to be 0 if you set this equal to the vector 0, 0. But if y is 0, plug in y equals 0 here and here, you get 0 there. Negative x would have to be 0, so x would have to be 0 as well. The origin is the only equilibrium point for this nonlinear system, and we are going to linearize at that point, or near that point. And when your equilibrium point is at the origin, linearization is pretty simple. You just get rid of nonlinear terms. When the linearization is not at the origin, it's more complicated. So here's what I got when I get rid of the nonlinear terms. I essentially just, in going from here to here, I essentially just crossed off the nonlinear term, so to speak. I'm ignoring it. These are different systems. This is a nonlinear system. This is the corresponding linearized system at the origin, where I get rid of those nonlinear terms. Hopefully, though, they're close together when x and y are close to 0. And yes, that is the key thing. These things are approximately equal when x and y are really small, like 0.1 or 0.01 or something like that. You might want to think about that. What's with this other notation? What's this L epsilon and this J epsilon? Again, don't worry about the epsilon at the moment. Think of it as fixed. Pretend it's a 1, for example. L is just emphasizing this is a linear function. In fact, it's a linear transformation. I could call it T, as I've often called linear transformations, but I decided to call it L because I'm going to make an analogy with something from Calculus 1 here. What's this J? J is honor of Jacobi, and this is called the Jacobian, or I should circle the whole thing. This thing is called the Jacobian matrix. We will see that the Jacobian matrix is really a kind of derivative of the vector field. Some people don't call it the Jacobian, some people call it the total derivative, some people just say this is the derivative of this vector field. Okay, our textbook by Blanchard, Devaney, and Hall calls it the Jacobian, so I will talk about it that way. I will use that terminology. Though you should be aware that the Jacobian matrix is related but different than to the Jacobian determinant, which if you've had multivariable calculus, you may have seen before when you do change of variables in the general case. There's something called the Jacobian determinant in that case. They are related to each other. The intuitive idea / reason behind the use of this linearization at the origin is what? It's an approximation, a linear approximation. Here's our nonlinear vector field, this whole thing here. If x and y are close to 0, there's your approximate equal to, get rid of the nonlinear terms. F is approximately L when y is close to 0. This is no proof, this is just an intuitive thing here. But it should make some sense, especially if you imagine plugging in pretty small numbers for x and y. You know, if x is 0.01, 10 to the negative 2, and y is 0.1, say, 10 to the negative 1, then these linear terms that you see here in the formula for f and also in the formula for L are small. They're on the order of these numbers. However, the nonlinear term, and in particular its second component, is a lot closer to 0. You might say orders of magnitude closer to 0. X squared times y, ignore the negative sign, would be 10 to the negative 2 squared times 10 to the negative 1. 10 to the negative 4 times 10 to the negative 1 is 10 to the negative 5. As a decimal, what would that be? Why 0? Let's see, what, four zeros in front of the 1? Yeah. Okay? That. On the order of 1,000 times smaller than x and 10,000 times smaller than y, or 10,000 times closer to 0. Think of it that way. So while both kinds of terms are small, the nonlinear terms are orders of magnitude smaller, you might say. And that's what intuitively justifies this approximation. In fact, we might even write derivative symbols here. So dy means derivative with respect to y, with respect to a vector, of the vector field evaluated at 0. Notice the vertical line, y equals 0. We could maybe even write boldface f prime of 0 if we wanted to. Or we could use this Jacobian notation, evaluated at 0, 0. Technically speaking, I could use any one of those three notations, but I will consistently use the Jacobian notation again, because that's what Blanchard, Devaney, and Hall's book talks about, is the Jacobian. Okay? But it is a derivative. It is a kind of derivative. It's a derivative that's really a matrix. It's this matrix. What? A derivative that's a matrix? Well, it's a matrix whose entries are partial derivatives, appropriate partial derivatives of the components of the vector field. That's what it's going to end up being. Also note that the vector field evaluated at 0 is 0, and that's again a reason why we can do this approximation. There's no constant term, no non-zero constant term in this vector field at 0, 0. All right, let's talk in terms of relating this back to chapter 1 next. Remember back in chapter 1 we talked about the one-dimensional version of linearization. I also called it the one-dimensional Hartman-Grobman theorem. There's a higher dimensional Hartman-Grobman theorem. I'm not going to state that in this lecture. I probably will in 1 or 2 lectures. It's not an easy thing to understand, but we want to maybe state it anyway and just try to get the basic idea that we're certainly not going to prove it. Okay, that's way beyond the scope of this course. What did the linearization theorem from chapter 1 say? It said, suppose y0 is an equilibrium point of an autonomous first-order differential equation. Scalar differential equation here, no vectors. dy dt is f of y. What did we do with this kind of thing? We made slope fields, solutions in slope fields. We also made phase lines by compressing the information in the slope field onto the y-axis, where we assume f is nice. F is continuously differentiable. It's differentiable, it's got a derivative everywhere, and that derivative is continuous everywhere. On some open interval near y0, it could be a small interval, but as long as it's some open interval containing the point y0, the initial value of y, then this is fine. We can linearize, we can look at the derivative of the right-hand side function at the equilibrium point. If the derivative is negative, then y0 is a sink. If the derivative is positive, then y0 is a source. And if the derivative is 0, then it's really not part of the theorem, but this is a comment. Then we need more information to determine the type of y0. Could it be a sink, a source, or a node? Before I move on, think about the analogy here with say, two-dimensional linear systems and eigenvalues. If both eigenvalues were negative, we saw that in two-dimensional systems that the origin was a sink. If both eigenvalues are positive, we saw the origin was a source. And other things could happen as well. If one's positive, one's negative, you get a saddle point. If they're complex, non-real complex, you could get spiral sinks, spiral sources, or centers. But it's still somewhat analogous in these two cases. Thinking about this is related to eigenvalues in the higher dimensions. In fact, you might say, if this were a linear system, a times y on the right-hand side, then a would be the derivative. As a 1-by-1 matrix, its own eigenvalue, and we'd have a negative eigenvalue, and it would be a sink, and a positive eigenvalue, it would be a source. If this was little a times y, where a is a number, or a 1-by-1 matrix. 1-by-1 matrix, its eigenvalue is itself, essentially. Since y0 is an equilibrium point, it follows that f of y0 is 0. That's important, because it means we can simplify the linear approximation from calculus 1. Remember way back, calculus 1, when you're trying to approximate a nonlinear function with a linear function, L standing for linear, that's why I'm using the L here. Here was the general formula. You may have seen this with the letter A used instead of y0. F of A plus F prime of A times x minus A if x was the independent variable. It's the same thing, just different letters here. F of y0 plus F prime of y0 times y minus y0. But because F of y0 is 0, because I'm at an equilibrium point, that term goes away, and I can simplify to just that. And this is a quote-unquote good approximation when y is close to y0. And this thing right here, this is a nonlinear function. This thing is a linear function of y. Not y0, but of y. y0 is fixed. This is a linear function of y. There's the slope. The derivative is the slope. And then this made good intuitive sense when we thought about phase lines to graph the right-hand side function, f of y versus y. And for example, if at an equilibrium point its derivative was positive, that meant for the phase line, equilibrium point at y0, solutions when y is just below y0 have negative slopes because the output of this function is negative, so you are decreasing. And solutions when y is just bigger than y0 have positive slopes because of the differential equation, and this function being positive when y is bigger than y0, so you have upward pointing arrows, and that's the intuitive justification for y0 would be a source in that case when the derivative at y0 is positive. What happens in higher dimensions here? It is the analog. We are still thinking about a nonlinear system, nonlinear differential equation. Oops, that was the wrong thing to do. I used a regular eraser on the whiteboard, but it kind of worked. All right, hopefully it didn't damage it. This is a nonlinear scalar differential equation. We can approximate the right-hand side, and that can give us an intuitive justification for this linearization. Here's a nonlinear vector differential equation, autonomous, with boldface y0 being an equilibrium point because the output of the vector field there is 0. It's just a dot that you would draw in the vector field at the point y0. In the previous example, y0 was 0. By the way, I do want to show you animations, more animations on Mathematica here before the end of this lecture, including what happens with the van der Pol equation. But let's save that for the end. These are pretty cool animations. You're going to want to hang on for it. I really like it. We can do something similar. We can say f of y is approximately L of y. This nonlinear function, this nonlinear vector field is approximately this linear vector field. But the linear vector field, by definition, is this, in general. The value of f at the particular point y0, which is our equilibrium point, plus essentially the derivative. The Jacobian is essentially the derivative times this difference vector. That's a 2 by 2, well, in the 2 by 2 case, this would be a 2 by 2 matrix times a 2 by 1 column vector is what it would be. This would be a matrix times a vector. But once again, we are in the case where f of y0 is 0. That can get substituted in here, and we can get rid of that term and just write it like this for vector y close to the vector y sub 0. Completely analogous, just higher dimensions. It's a number times the difference of two numbers. This is a matrix times the difference of two vectors. In the general case, it would be an n by n matrix times an n by 1 column vector, giving you an output that's also an n by 1 column vector. So symbolically, it should make intuitive sense. Let's try to apply this here in a minute. Before we do that, I want to say one more thing. This is usually good enough to classify the equilibrium point of the nonlinear system at y0. Usually good enough to classify the equilibrium point for the nonlinear system. What nonlinear system? That one right there. Near the equilibrium point. Is it a sink, a source, a saddle? spiral sink, spiral source. It's usually good enough. It's not always good enough. When is it not good enough? It's not good enough if any eigenvalues of this matrix are 0. It's also not good enough if any of the eigenvalues are pure imaginary with 0 real part. So the problem is, if you graph the eigenvalues in the complex plane, real axis, imaginary axis, you have problems if any eigenvalues are on the imaginary axis exactly. That's when this doesn't work. Unless it just happens to work by accident, so to speak. But there are plenty of examples where it doesn't work and you can't make a prediction for sure. Because different things can happen. Okay, we will see that. All right, let's apply this now. After I take a quick drink. We're going to apply this to a competing species model. Nonlinear. Parameter mu. Here it is. Think about this with me here. So we got two species, x and y. These are functions of time that represent populations of two species. We'll call them species x and species y. Focus on x's differential equation first. When y is 0, this term goes away, and you're left with dx dt is x times 70 minus x. Back in chapter 1, we learned that that is really a logistic model with a carrying capacity of 70. Think about the units here. It could be, say, 70,000. Units of x could be in thousands, for example, or maybe even 70 million. But then we subtract x times y. That's called an interaction term. And when its coefficient is negative, in this case negative 1, that's saying the growth rate of x, dx dt, is negatively affected by the presence of species y. When x is present and y is present, we're subtracting a positive product here, so we could possibly get a negative derivative. It's possible, depending on what x is over here. And what x times 70 minus x is. Is it positive or negative? And how, if it's positive, how big is it? The dy dt equation is similar. The interaction term has a coefficient of negative 2 instead of negative 1, just to change it up a little bit. The other thing that's different is you got a carrying capacity equal to mu, this unspecified parameter. I wonder if this is a bifurcation problem. It is. So we're dealing with two things at once here, linearization and bifurcations. You might even say we're dealing with three things at once. We need to draw phase planes, perhaps. But before we try to draw the phase planes, it'll be good to find the equilibrium points and linearize near them using the Jacobian matrix. That's where we're going. As a vector field, you could write it like this. It's autonomous, no t's on the right-hand side. For the purpose of finding the equilibrium points, it's a good idea to factor the right-hand side functions that are called little f and little g here as much as possible. And it can be done. The f term has x in both spots. The x can be factored out. The dy dt equation involving the function g of xy has a y in both terms. A y could be factored out. That's going to help us solve for the equilibrium points. Okay? There are going to be 4 of them here. 3 of them are pretty easy to find. The 4th one takes a little work. Look at this system of nonlinear equations. What are its solutions? Well, certainly if x and y are both 0, that works. The origin is an equilibrium point. That represents no species. X is 0, y is 0, always. You're assuming they're not introduced into the environment. So certainly 0, 0 is an equilibrium point. What else? Well, are there any equilibrium points along the x-axis where y is 0 that are not at the origin? If y is 0, that certainly makes this equation true. And if you plug in y 0 equals 0 right there, that term goes away and you're left with x times 70 minus x, which means x is either 0 or 70. We already talked about the case where x is 0 at the origin, so another point is x is 70, y is 0. That's a second equilibrium point. I will show you them here in a second. A third equilibrium point would be on the positive y-axis, when x is 0. When x is 0, this equation is certainly true, and when you plug in 0 there, this term goes away, you're left with y times mu minus y, which has solutions at y equals 0 and y equals mu. We already dealt with the one at the origin, so the other one on the y-axis is at x is 0, y is mu, which changes as mu changes. It would go up as mu goes up. The equilibrium point would change as the parameter mu changes. The final equilibrium point would be where both of these things in parentheses are 0. And that's a linear system of equations. You could solve a linear system by row operations if you like, but it's not really necessary. It's equivalent to x plus y equals 70 and 2x plus y equals mu. And so, for example, if you subtract the first equation from the second so that the y's cancel and 2x minus x becomes x, you get x is mu minus 70. I subtracted the first equation from the second. This one minus this one to cancel the y's. This is a y here. And if x is mu minus 70, I could then use this equation to solve for y. Y is 70 minus x. That's going to be 70 minus, in parentheses, mu minus 70, which is 140 minus mu. And the point with those coordinates is our fourth equilibrium point. There they are. All right. What do we want to do next? Linearizing. Find the Jacobian matrix. Do not just get rid of the nonlinear terms. That only would work for the origin. Here's what the system looks like when you expand it. The nonlinear terms are these four terms here. If you got rid of those, that would linearize, be the linearized system at the origin. dx dt is 70x and dy dt is mu y. And if mu is positive, that would mean the origin is a real source. Two positive real eigenvalues. It would be a diagonal matrix. But that getting rid of nonlinear terms like that doesn't work at the other equilibrium points. You have to use the Jacobian matrix. Or, as maybe I'll show you next time, you could do a change of coordinates that involves a translation. We haven't done translation change of coordinates before. The Jacobian matrix is this matrix. I haven't defined it yet. Now I'm defining it. Jacobian matrix, J of xy, is this, in this case, 2 by 2 matrix. First row is the derivatives of the first function, right-hand side function, little f, partial derivative of little f with respect to x, partial derivative of little f with respect to y. When you calculate those derivatives, it's best to use this form. When you calculate the derivative with respect to x, you just treat the y as constant. Differentiate this with respect to x is going to give 70 minus 2x minus y. Which is exactly what you see right there. 70 minus 2x minus y. Differentiate with respect to y, treating the x as constant. Differentiates to 0 minus x. Treating the x as constant there, like a minus 5 or something, times y. The derivative would be minus 5 in that case. The derivative of this with respect to y is negative x, which is what you see right there. Second row is the derivatives of g with respect to x and then with respect to y. Differentiate with respect to x, treat the y as constants, those go away to 0. This differentiates with respect to x to give you negative 2y, which is what you see there. And then finally in the lower right corner, differentiate g with respect to y. You're going to get mu minus 2y minus 2x. Mu minus 2y minus 2x, I put them in the other order there. That's our general Jacobian matrix. It's a matrix-valued function of x and y. For a given point in the xy plane, it gives you a 2 by 2 matrix. But we only plug in equilibrium points. Don't plug in other points, okay? At least in this class. That's all we really care about is plugging in equilibrium points. Let's use it now. Now evaluate the Jacobian matrix at each equilibrium point. Then use linearization to classify, when possible, the corresponding equilibrium points for the nonlinear system. When possible, when is it possible? When eigenvalues have non-zero real part, which includes being non-zero itself. So as complex numbers, which includes real numbers, the real axis is horizontal in the complex plane, the vertical axis is labeled imaginary. As long as none of your eigenvalues are on the imaginary axis, which means they're either pure complex, pure imaginary, I should say, like plus or minus 5i or something, or 0. We don't want that to happen to be able to use linearization. All right, so here it is, step by step. Equilibrium point 1, when we plug in the point we get this, I should probably write down the Jacobian matrix on the board here, so that you can refer back to it. J of xy in general here is this 2 by 2 matrix, 70 minus 2x minus y in the upper left, negative 2y in the lower right, mu minus 2x minus 2y in the lower, that was the lower left, excuse me, lower right, negative x in the upper right. I'm sorry if you can't quite see this. Let's move it over. 70 minus 2x minus y, negative 2y, mu minus 2x minus 2y, and negative x. All right, there's our general Jacobian matrix. Now plug in the equilibrium points. 0, 0. The off-diagonal numbers become zeros. This becomes a 70, this becomes a mu. Exactly what you see here. It's a diagonal matrix. The eigenvalues in the main diagonal, they're 70 and mu. And we were assuming mu is positive, so those are both positive real numbers. So the origin is a source for all positive mu. Equilibrium point 2. Plug in x is 70, y is 0. 70 minus 140 minus 0 is negative 70. Negative 70. 0. Plug in x is 70 there. Negative 2 times 70 is negative 140. 0 there. You get mu minus 140. That's not diagonal, but it is upper triangular. The eigenvalues are still the numbers on the main diagonal. It's negative 70 and mu minus 140. So what kind of point is that? Well, it would depend on mu. If mu is less than 140, so that this number is negative, then we'd have 2 negative real eigenvalues. It would be a sink. On the other hand, if mu is bigger than 140, then you've got a negative eigenvalue and a positive eigenvalue. The origin is a saddle point. Equilibrium point 3, at 0 mu, plug in x is 0, y is mu. Try it. You'll get this matrix. Not diagonal, not upper triangular, but it is lower triangular. The eigenvalues are still on the main diagonal. They're 70 minus mu and negative mu. This is 2 numbers here, 70 minus mu, comma, negative mu. So it still depends on what mu is. It's going to be a saddle point if mu is less than 70, like 50 for example, then you'd have a 70 minus 50 is 20 and a negative 50, opposite signed eigenvalues, it would be a saddle point. If mu is bigger than 70, like 80, you have negative 10 and negative 80, 2 negative eigenvalues, it would be a sink. Fourth equilibrium point, you should check that you get this. That's not diagonal, it's not upper triangular, it's not lower triangular. So what do? We could try to find the eigenvalues in terms of mu, but it's better, easier to use the trace determinant plane. Find the trace and determinant. The trace is the sum of the numbers on the main diagonal. Add those up, the mu's will cancel, giving you 70 minus 140 is negative 70. Find the determinant, it's the product of these two things, minus the product of these two things, and I factor it out of 2, because essentially now you see that these match. Giving, this is a typo here. No, it's not a typo, excuse me. I was thinking there's a minus sign missing, but I switched around the 70 minus mu to be a mu minus 70, so this is correct. So the trace is negative 70, and the determinant is a function of mu. In the trace determinant plane, we're going to be along a vertical line at t equals negative 70 as mu changes. You can move up and down that vertical line as mu changes. You're either going to be at a saddle point or at a sink, based on the trace determinant plane. It's not clear whether you might get a spiral sink or not, and we're not going to talk about that right now. It's some kind of sink, maybe spiral, maybe not. Actually, I think mostly it's not. When mu is less than 70 and bigger than 140, and it's a saddle point when mu is between 70 and 140. The motion along that line in the TD plane is not in one direction as mu increases. D, when mu is less than 70, for example, going to be the product of 2 negative numbers, which is positive. You're going to be up here at first, and then as mu increases, you'll go down here. But then as mu increases some more, you're going to go back up there. So you go from a sink to a saddle back to a sink again, as mu continues to increase. Also note, however, but as far as the application goes, we're talking about competing species. X and Y can't be negative. Then this point, this fourth point, is actually only in the first quadrant where it's realistic for the model when mu is between 70 and 140. So that means for the most part we're thinking about the fourth point being a saddle point. Here's a static picture of the phase plane that I drew with Mathematica, and then at the very end I'm going to show you Mathematica here. There it is. And let's just quickly say we see the origin as a source. I did include negative values of x and y a little bit in the picture because it just makes the picture look nicer. And you see more completely as far as the math is concerned. The origin is a source. This point here and this point there are sinks, and this point is a saddle point. The saddle point is the hardest one to see. You'd have solutions that are maybe right around here that would head toward the saddle point, but end up above it and cross this null line, which is in pink there, and head up this way. If your initial conditions are lower, like here, you'd be doing something more like this. Down here, if your initial condition was here, you'd go up like this and head toward this point as t increases. Down here, something similar would happen. And I made a mistake just there. Those solutions should not cross each other. This is an autonomous system. Solutions can't cross. There is a solution that starts at this point, so to speak, when t is minus infinity. It ends at this point when t is plus infinity. Now, minus infinity and plus infinity are not numbers, so that's not a literal description of what happens. Really, this is a solution curve that approaches this one as t goes to minus infinity and approaches this one as t goes to plus infinity. There's another one that approaches from this direction as t goes to plus infinity and heads off to infinity as t goes to minus infinity. So there's a real quick picture of what the phase plane looks like when mu is 100. Let's end by quickly looking at a bit of Mathematica. It's a longer lecture here than usual, but I think it's worth it. Here's syntax for the van der Pol equation, by the way, and its phase plane. Well, let's do it this way. Oops. Great, I have to, problem here. I need to enter this first. I used NDSolve again. So this is the van der Pol oscillator, starting when epsilon is 1, but if I change epsilon to be negative, then the origin changes from being a spiral source to a spiral sink when epsilon is negative. That's interesting to think about. It doesn't have the application to the electric circuit that way, but it's interesting to think about mathematically. Letting t change does allow me to see my solution curve, which does approach a periodic solution when epsilon is positive, and we saw this kind of picture before, and I can change my initial condition with the locator. And no matter what initial condition I take, when epsilon is positive, we approach that periodic solution. And then this is for the competing species. This is for the equilibrium points right there, and the phase plane. And I've got the Jacobian matrix in there as well, but here's an animation of the phase plane. As mu changes, we see the equilibrium point, for example, the y-axis going up. We see the other one that goes along the brown line. That's the one that's in the middle when mu is between 70 and 140 there. The null line changing is what's causing that changing behavior. And this does the Jacobian matrix, and we can see what it is in each case. And that's the end of lecture 30A. Hope you liked it.